In this video, we will be discussing on the intriguing phenomenon of the hydraulic jump, a fundamental concept in open channel flow. A hydraulic jump is characterized by an abrupt transition from a high-velocity, shallow flow regime, supercritical, to a low-velocity, deeper flow regime, subcritical. This rapid change is accompanied by significant energy dissipation through intense turbulence and the formation of a characteristic roller. We will delve into the underlying principles governing this transition, examining the conservation equations of mass and momentum that dictate the relationship between the flow properties upstream and downstream of the jump. We will also discuss the dimensionless numbers, such as the Froude number, that predict the occurrence and characteristics of hydraulic jumps. Furthermore, we will explore the practical significance of understanding and predicting hydraulic jumps in various engineering applications, including the design of energy dissipation structures, flow measurement devices, and the analysis of flood wave propagation. By the end of this presentation, you will have a foundational understanding of the mechanics of hydraulic jumps and their relevance in hydraulic engineering. The diagram presents a schematic representation of a hydraulic jump occurring in an open channel. The flow transitions from left to right, clearly depicting the change in flow characteristics as it passes through the jump. The diagram highlights key parameters and flow regimes associated with this phenomenon. The arrows indicate the flow is moving from left to right. A hydraulic jump is a phenomenon in fluid dynamics where a fast-moving, shallow flow of liquid I.E supercritical flow abruptly transitions to a slower-moving, deeper flow I.E subcritical flow. This transition results in a sudden rise in the water surface, accompanied by intense turbulence, energy dissipation, and mixing. Supercritical flow occurs when a liquid flows at a velocity greater than the wave celerity I.E speed at which disturbances propagate. This means that downstream disturbances such as changes in depth or obstacles cannot travel upstream. The key features of supercritical flow is the flow is fast and shallow compared to subcritical flow. The Froude number is greater than 1. Subcritical flow occurs when a liquid flows at a velocity slower than the wave celerity, meaning the speed at which disturbances propagate. This means that disturbances such as changes in depth or obstacles can travel both upstream and downstream, allowing the flow to adjust gradually. Here, the flow velocity V2 is lower than the wave celerity, allowing disturbances to travel upstream. Characterized by a relatively deeper depth Y2, and lower velocity V2 compared to the upstream flow. The Froude number Fr is less than 1. This is the central feature of the diagram, depicted as a region of turbulent, rapidly rising water surface. It represents the transition zone where the high-energy supercritical flow abruptly changes to a lower-energy subcritical flow. The transition from supercritical to subcritical flow, the abrupt rise in water surface, the turbulent nature of the jump itself, and the change in flow depth and velocity across the phenomenon. The inclusion of the Froude number as a defining characteristic of the flow regimes is also crucial for understanding the underlying fluid dynamics. Hydraulic jumps have numerous practical applications in hydraulic engineering, environmental management, and industrial processes. Two of the applications are the energy dissipation and erosion mitigation. Hydraulic jumps are widely used to dissipate excess kinetic energy in flowing water, preventing erosion and damage to downstream structures. For spillways of dams operation, after water flows over a spillway at high velocity, a hydraulic jump is induced at the base to dissipate energy before the water reaches the riverbed or stilling basin. Specially designed basins are constructed to create hydraulic jumps for controlled energy dissipation. In irrigation canals or drainage systems, hydraulic jumps reduce the erosive force of high-velocity flows. Hydraulic jumps are also used to control and stabilize high-velocity floodwaters, reducing their destructive potential. The hydraulic pattern helps reduce the velocity of floodwaters, minimizing erosion and structural damage. In addition, in flood management system, hydraulic jumps are incorporated into stormwater management systems to handle peak flows safely.